Okay, so now is time for Dr. Armin Wedler from DLR. He is the head of the exploration and the robotics section in DLR, and he's going to present the lesson learned from the ARCHES deep sea and space domain.
Thank you, Miguel. Thank you, David, and all the audience for having me here. And yes, as you said, I will give a brief overview. 50 minutes is very short, and I had already some recaps of this mission. So I'm very proud to present here the work of our analog campaign we did with 50 people, approximately 1 month on Mount Etna. And I will try to give some insights on some techniques we used, but I will also, let's say, try to give you some ideas of our lessons learned and what I learned, let's say, or my team people learned. So the overarching project we have is ARCHES, which is a combination of research in deep sea and space exploration. We have the overarching idea that very challenging domains where humans are very complicated to be in action. So we send robots over. The goal is to have cross-domain development, technologies, methods in developing autonomous systems, cooperation of robotic network teams which work together. So we have different heterogenic team members, which in both mission parts. So we had a demonstration mission on the Arctic Sea, and we had a demonstration mission on the Mount Etna as an analog for space environment. We did researches in navigation, in mainly mission operation, which will be also a key of a little bit the focus of this talk today here, since we have the group here of the heterogenic teams. So that was our environment and our site on Mount Etna on 2,600 meter height. So a very beautiful site, but also a very analog site, and I would say very nicely representing Martian lunar surface, since we have all this regoliths or this fresh lava flow here. We built up a communication center in Catania, so we really, let's say, simulate a mission. We communicate from Catania up to the mountain, around about 23 kilometers, and we had a direct link. So we really simulate mission operations. So this simulation was not only robotic technologies and robotic technologies and methods. It was also involving the mission operation, which I consider as a very much benefit, and we learned a lot of it. To having scientists down in the room, we had Thomas Reiter operating over robots, so we had real astronauts involved, but we had also, let's say, non-technician, which is, I think, a big lesson learned. We had two real, or let's say 3 separate real mission applications. One was dedicated to geological exploration, and one was dedicated to a permanent installation on the lunar surface, which we call it the LOFAR installation, but somehow we deployed on the area of our site a LOFAR antenna, which was really functional. So all what we present here is really functional, and we have used instruments which are really functional. And I would say that the geological exploration is one of the key targets if you look for either EL3 missions, or let's say all other missions. I would say picking up samples, collecting samples, doing in situ analysis is one of the next mission targets. And the future, building up a LOFAR on the backside of the moon, is a big idea of a lot of scientists. So this graph just shows that our team members in the exploration, so there was the ESA Interact rover here, our 2 LAUs, our drone, and a scout rover from the SR team. And we also have the Rodin lander, because we had implemented some intelligence and communication in the lander, so I will consider him as a team member. We had a lot of tools. So one of the key message I would like to give you, I think we invest a lot of time and also engineering costs in an interface which allows us to transmit power, mechanical, and also signal communication to tools. So we are able to exchange our robots in the capabilities. Sorry, that was too fast. Towards either these tools I just showed, but also different kind of toolboxes, which we configured. We had at Etna 26 of these toolboxes. So there were battery toolboxes, there were communication relays, and I think also in the DARPA challenge, there were some aspects, or that they use different boxes, of course, but we all interface it. So the ESA rover could pick up one of this box and we could drop it down. And I think there will be also Emmanuel's talk later, talking about this radio communication here. and yeah, some other talks here. So we did investigate a lot of this kind of aspects, and I present some papers here to refer to you at ESC. I think we presented in more than 3 papers. And this is something I would like to show you because we put it also open source. And I think when we talk about this heterogenic aspect, that's the key, in my understanding at least. So we have a little bit of different aspect that, or approach than what was presented before. So we do not have a centralized unit which collect everything. We have everything collected on its robot itself, and it can call the other robots to get more information. And what you see here is our, let's say, mission control setup on the expert level. So we have a different GUI for the scientist, and we have a different GUI also for the astronaut operator. But this is an expert tool where you can select in the map on ARCHES module. You can select a task you want to do. For example, collect a sample or do an eSRO analysis with a LIPS instrument, and then on the right side, the command window is executing the subsequence of the autonomous sequence on its robot itself. So it distributes the task. If you choose, for example, collect sample, of course, it can only be a robot which does a task which have a collection capability. So that's considered inside here. So that's a detailed view on the GUI we're doing. And that's a detailed view on this mission task distribution service. And it's including and it's combined with all orientations, with all subsets of this autonomous subsequence. So we call that skills, right? So, well, this is a system overview, very good. And it communicates, that's maybe important. So we have this communication, this mission control service on a higher level. On a lower level, we have a RAFCON, which is this task execution, autonomous task execution. And all of these things are open source, and we put it free, and we would be happy if many people use it, and we get feedback for it. At the end, I will show you where you can find all this information. Then I will go a little bit on detail how we really use one of these instruments. So we had a LIPS instrument, let's break down spectroscopy, which was implemented in the box here. And the autonomous task setup was, let's say, if you want to execute this LIPS instrument, you will receive such a plot of the point where you do the experiment, and then scientists, and we had this scientist team. So Susanne Schröder from DLR in Berlin is part of the ChemCam team here. So an expert in LIPS, I would say, and Rahman and Fabian was also involved in her team. And they were deciding it. And the loop, so for example, we analyze in situ, and we decide that we would pick up the stone, would make the loop almost autonomous. And we do not want to substitute the scientists. We do not want to substitute the astronaut, which is a bad idea, I think, in robotics. We want to include them, but we don't want to, give them a Cartesian interface. We want to give them an easy to use interface, and that's the approach you can see here. And that comes to the subtasks which are involved in this submission. I will just show the video which combines all of this. So now we go a little bit deeper in all this subsequence of the missions. So you can see all sequence. I mean, at the end there's executed code, but somehow we have the snippets, and we can copy paste the snippets toward another mission, toward another use case. And this is how it looks like. Unfortunately, I'm not really sure how much faster it is in real time. I think 20 times, but I'm not sure. This mission approximately takes 2.5 minutes. So this sequence of the mission. So we pick up the LIPS instruments from the back, we put it on the stone, and we fire it, and we get a signal back. And then the instrument output is sent down to the robot. Since we are at the recap session, I also want, we had a summer school with 50 people on Vulcano, so we educate. So the idea of us is, if we do such missions, we try to benefit the community. So we put a lot of things open source, but we also try to educate. So there was a professor from the Jacobs University in Bremen, which was educating 50 young talents, young students to come over. And they were next to us, but they have their own mission. So the summer school was connected to the Etna part, and it's like on an island, volcano island, beautiful island as well. And they were joining us for 2-3 days. On the other side, they were independent. This is a recap of let's say, the overall mission approach, and you can see this beautiful but also very analog environment on Etna. And I will just speak about it. So one lesson learned is also that bringing 50 people to such a mission is a lot of things goes wrong, and it's a lot of logistics. It's a lot of technical research, non-scientific methods. It's just dust. All computers are full of this powder, and our admins are also quite unhappy about cleaning them up. But somehow this is what all you get. But I think it will worth the time and worth the money to do it, because again, lesson learned. That's the workshop on the lesson learned, and I think we learn a lot from especially the other domains. So the scientists, these operators, that's so valuable, because we technicians, we like to go deep in our research, and we like to work very close with technical problems and planetary exploration robots in an autonomous manner. I think that's what you learn a lot. And also with this ESA team, different DLR teams, and a lot of participating teams, I think we had a lot of exchange by having those people solving one problem, this mission together in this period. So that was in my outtake, I think, the best benefit, and I really recommend everybody to bring the stuff out. You do try to really do it. So I also very much appreciate the DARPA challenge approach. That's very big achievement just presented before my thing. So this is outside, it's not in a cave. So for example, here you have multi-robot cooperation. The inspector with a science cam, so that's a copy of the PanCam of ExoMars, but also the science cam is detecting a stone, is doing a spectral analysis of the scenario, and the scientist is then choosing the stone to pick it up, and the robot with the arm is picking up the stone and bringing it back. And all subsequents are really fully autonomous. You see a differential GPS navigation on the thing is only to reference. So we put like 4 papers out, I think, currently on our navigation system. And we put also a lot of data sets, I will come to it later, which are available for you in ROSPEC files. We took a lot of time to prepare them, to make them available and bring them back. So due to time, I will go quickly on about some impressions. So nice photos, a lot of engaged teams. That's something I always put because I think it's important, and I think it's also something I'm currently working with ESA also together to bring a capability of exchanging data. I mean, it's not easy to host data sets which are 1 tera, 2 terabytes, to make them downloadable for people, for a lot of people. So behind this, 4 data sets, they're around about 8 terabytes, and you can download them with a download manager, and it's not easy to find such solutions. So, and I think that's important to bring them to people out. It's also a lot of work to prepare these data sets, because if you just, put raw data, probably it's not readable for others. So I would point a lot to this work, and I think that's also the message we have, and the work I believe our team is doing. So very quickly just said that, I mean, the idea, we had this mascot mission in DLR, so we're really doing space flight mission. We had developed this small robot. We did this ARCHES mission, and we are currently in some year 3 programs, and you all know that's very challenging. And yeah, obviously Ishida's also here. So we are with Japan. So we're very proud to be part of the MMX team. So we are developing with the CNES together a rover, which is currently in an so the flight model is made in our institute with a lot of DLR parts, and Raman instrument is on it from Susanne Schroeder as well. And we are developing this, yes, 35 kilo, I think it's something like this now, little small robot to go on the Martian moon Phobos. And yeah, thanks for your attention.
Thank you very much, Armin. Amazing work. Yeah. So if there are any question in the audience? To impress.
To impress.
Okay.
Anna, maybe. Okay.
Yep.
So how big of a challenge was it interconnecting so many teams with different hardware? Can you comment on that? Was it done on ROS basis, or what was the interlink between the teams and robots?
Yeah, that's a very good question. In terms of, I have to say, beneficially for us, a lot of DLR members, we had already used and integrate them beforehand. So it was mainly done on the communication layer. So that's Robert Pollmann here, also from the KN Institute, and I think Emmanuel will talk. I don't know if he talked so much on the communication aspect, but we have the same Wi-Fi. We exchange maps, for example, in graph-based on graph-based system. Our systems, let's say, which were in the core team of the DLR development, so the ESA robot, I have to say, was not sending fully data. So we had therefore to combine the scientific exchange. We had a server which was collecting all scientific outputs from the site, which we then in a GIS system, we mapped them together, put them in one global map, which was accessible for the scientists and the operator. The real, let's say, navigation mapping cooperation was done, as I mentioned in my question a little bit before. We have not a centralized unit, so a robot, if he approach an area which he doesn't know, so we have this, we don't have no idea of the environment, so we have a black map, let's say, and by exploring the environment, we build the map. And before he explore an unknown environment, he asks the other robots if there is some information already, and he get graph notes back from the other robots. So he can increase his knowledge by asking the other robots on this exchange. And this is done, I mean, this is controlled, let's say, by this ROS-MC, which I present, and is done by nodes in RAFCON. We have an exchange on nodes and ROS, so we have an interface to ROS. So ARVIS, for example, we use from ROS. I hope this answers the question. It was a bit wider. I don't know.
So you said that each robot has its own map.
Mm-hmm.
And do you share the map with the ground station, which is like 23 kilometers away? And if so, did you have any struggle to communicate with the ground station? Because like the map and the point cloud are usually very heavy, and 23 kilometers away is very long distance.
Yeah.
So
yes and no. So we have a that's what I said also, for example, the Rodenländer was a communication relay. So if one robot requests a map, we didn't send the point clouds. That is too much on data. We communicate on graph on a graph representation of the area. So, and then he can request more details. For example, if he would like to approach a crater, or so, he can request more details from the robot, which is known that the graphs shown that he have more details. And this is done between the robots. And in our case, the communication would go over the lander, not over the ground station. And the ground station is collecting all data depending on its communication capability and for representation of the operator state. Does it answer your question? Yeah, good. Hendrik.
Yeah, you also showed this the task scheduler, and you mentioned that this is something that you also want to open source or like make available. How would you foresee, how difficult would it be to add another robotic system And you use it.
In profilers, for example. Yeah, I mean, Rio is here and have a paper down, so I want to point to him, but I don't see him in the room. That's Rio. That's Rio. That's my colleague or team member, and he developed this ROS-MC, so we can discuss it in detail with him later. And I think it's possible, Rio. We can implement all robots. It's just some time of a very busy employee. Very good. Again, it's open source. It's also worth if you have a look in it, and we would appreciate, Rio, if other people use it. And yeah, I think for profilers, if we need to talk about it, if you have more information on it, but somehow we could look at it and try to use it. Okay, I think we need to close it now. Yeah.